Hello, welcome to the next homework video. We're still dealing with the homework on page 60. These numbers, we're on to problem number 55. So, problem 55. A connected graph H has a spanning tree with 26 edges. How many vertices does it have? Well, it has to have one more vertices, so 27 vertices. If that's not clear, go back and listen to the last video, problem number 54. I think I give an example that makes it fairly clear. And if it's still not clear, bring the question into class. I'd love to talk about it. How many vertices does H have? How many vertices does H have? Well, if there are 27 vertices in the spanning tree, there have to be 27 vertices in H also. So I can just repeat that. What can one say about the number of edges H has? Well, I don't know how many edges H has. If it's a connected graph, it must have at least 26. And I guess in order to have a spanning tree, it must have at least 26, because the spanning tree would have 26. But the number of edges, well, that first vertex, I would have 26 places to connect it, plus the next vertice, I would have 25 possible places to connect it. The next one, 24. And I would go all the way down to one of the vertices would have 2 places, another one 1, and that would be it. We have another way to write this that you actually don't have to know for class. But this is a summation. We're adding a bunch of numbers. There's a symbol for a summation. We use a Greek letter, sigma. It looks like that. And we want to sum all the numbers from 1 up to 26. So we say we sum from n equals 1 to 26. And if you just wrote this, it would mean the exact same thing as these. You don't have to know that, but there it is. Problem 56. A large company wishes to install a pneumatic tube system that would enable small items to be sent between any of 10 locales, possibly by using relay. If the non-prohibitive costs in $100 increments are shown in the graph model below, between which sites should the tube be installed to minimize the total cost? Well, if we can relay from one site to another, then this is a spanning tree problem. So I will take the cheapest edge, which I think is weight 3 right here. That's the only 3. After that, I'm going to take 4 there and 4 there. So 4, 4. Next is 5 here. Is that the only 5? I think so. Then I have 6. And I have a 6 over here. I have a 6 here, and actually I will take that. Then 7 takes me to a new vertex out there. 7 here would make a circuit. I already have both vertices on the sides of that edge, so I will not choose it. Same thing up here. This 7 would make a circuit, so I will not choose that 7. 8, I could do this, and that is a spanning tree. So this is what the sides they should choose, and it doesn't even ask what it'll cost. So that's it. That's our spanning tree. Question 57. If the weight of each edge in exercise 56 is increased by 3, will the tree that achieves minimum cost for the new collection of weights be the same as the one that achieves minimum cost for the original set of weights? So if everything here went up by 3, would I still make the same choices, basically? Well, if it all went up by 3, this would cost 6, but this would cost 7, and that would cost 9. So this still will be the cheapest edge. I would still choose that first. These 4s would be 7s. They would still be the next cheapest edge, and I would choose them next. What I'm getting at is that the choices I make would not change, even though every choice I make is worth $300 more, because they're $100 increments. $300 more than it was in the original problem. So, will the tree that achieves minimum cost be the same? Yes. And it doesn't even ask why. It just is a yes or no question. 58. Give examples of real-world situations that can be modeled using a weighted graph for which finding minimum cost spanning tree for the graph would be of interest. Most of the applications that are interesting with trees have to do with family tree type of things, like family trees of historical documents to assess how reliable one is, or things like that. But those aren't minimum cost spanning trees. Minimum cost spanning trees, we've given some examples in class, like the sprinkler system, like the pneumatic tube, like computer networks. We would be looking at that, like cell phone towers and where we're going to install them. And a lot of that with bandwidth will be changing in the future because they won't have to be connected through ground wires. But I think we've given lots of examples of real-world situations of these in class. If you need more, come and ask me. Question 59. Can Kruskal's algorithm be modified to find a maximum weight spanning tree? Well, yeah, of course it can. One way we could do it would be choose the most expensive edges instead of the least expensive. Instead of the least. And that would be just fine. That would work. There's actually another way that you could think about this. If I multiply all of the weights by -1, so if I have something here, and I'm going to make it really simple. If I have that, and I'm trying to come up with a spanning tree, and it's, I don't know, 1, 2, 3, and 4. If I want to find a maximum weight spanning tree, instead of just choosing the most expensive edges, I can multiply everything by -1, and now my weights are -1, -2, -3, -4. Now I can still just choose the least expensive, so I could run Kruskal's exactly as it is. The least expensive here would be -4, the next one -3, and the next one -2. Which, coming back to our original problem, is the most expensive spanning tree. So that's another way we could do it, is just multiply the edges by -1 and then apply Kruskal's as it is. Can you think of an application for finding a maximum weight spanning tree? Well, sure. Instead of minimizing, like here we want to minimize cost, I would want to maximize some sort of income, whatever that income would be. So maybe I'm working at some sort of business where edge weights are income. Maybe those are government subsidies I'm going to get for doing things. Maybe they're, I don't know, but any sort of income would work. Good. 61. Would there ever be a reason to find a minimum cost spanning tree for a weighted graph in which the weights on some of the edges were negative? And would Kruskal still apply? So, sure. If some weights were negative, I could think of this as maybe I have government subsidy stuff going on. And maybe I have some sort of graph like this. The weights are some are positive, and the weights on others are negative. Things like that. Well, maybe this is positive numbers are the income that I'll get, and negative numbers are, instead of income, are cost. Like these edges might cost more than I'm going to make for building them. So all of these edges could be profit instead of cost or income. If I had something like that, then I might have some negative weights and some positive weights. And Kruskal's algorithm would still apply as long as the negative weights are the most desirable edges, because that's what Kruskal's does. Otherwise, I could multiply everything by -1, and then these would be positive, and my negative weights then would be the most desirable sides. So that's the important part about Kruskal's, is you're going to choose the lowest weights first, so those should be the weights that you want. Problem 63 is down here. Two spanning trees of a weighted graph are considered different if they use different edges. Show that the following graph has different maximum or minimum cost spanning trees, though the different trees have the same cost. So, I think we ran into this issue on one problem. I don't remember if it was a previous homework or a previous video for this homework, but there was a problem that had two edges of weight 2, and it made no difference which one we chose. Oh no, there were 4 edges of weight 2. Anyway, here, first I would want to choose all of the ones. Well, there's a whole bunch of them, and these 3 make a circuit, so I'm definitely going to choose that. But between these 3 edges, I can choose any 2 of the 3. So maybe this time I'll choose that one and that one. I don't want this one because it makes a circuit. So then I would move to the next cheapest, which is 4, and then the next cheapest, which is 5. there's a spanning tree. If instead I started with choosing these 3 edges, next I would choose 4, next I would choose 5. These are different minimum cost spanning trees, but since my edge weights are the same, and 1, 1, 1, 4, 5, they both cost 5, 9, 10, 11, 12. So they both cost the same, even though both are different trees. That's fine. Last problem, number 65. Last problem for this homework. Determine whether each of the following statements is true or false for a minimum cost spanning tree T for a weighted connected graph G. So these are just in general. I have some spanning tree T that's inside, it's a subgraph of graph G. T contains the cheapest edge in the graph. Well, sure, that's how we build minimum cost spanning trees. So we start out with the cheapest edges. That must be true. B. T cannot contain the most expensive edge in the graph. Well, that's also true. Under no circumstances would we choose the most expensive edge. As opposed to a Hamilton circuit, where in Hamilton circuits we're forced into some choices. And when we're forced into some choices, we might choose the most expensive edge. But with spanning trees, we're not forced to make any choices. C. T contains one fewer edge than there are vertices in G. So if G has 4 vertices, then my spanning tree has 3 edges. Well, that's definitely going to be true. There is some vertex in T to which all others are joined by edges. So some vertex in our spanning tree to which all others are joined by edges. With edges being plural, I would say that this is true. But if you took edges to think like there's some vertex that everything is connected to by one edge that goes directly there, you could have said false. I would say with edges plural it's true, because if you look back, we have a whole bunch of examples here of spanning trees. Well, we could have something similar to this. If you had one edge, everything there does connect back with one edge if I delete the one with my fingers over. But not all of these, generally that's not the case. If there are multiple edges, they're all connected. So yeah, I can get anywhere as long as I use multiple edges. Part E, there is some vertex in T that has valence 3. Well, again, if I look back to all my examples here, that is sometimes true like here. Oh, that's 4. Sometimes true like here, but generally there's no reason that it has to be true. So E would be false. Thanks a lot. Have a great night.